We remember earlier in the course that we talked about gases, and one of the things that we said about gases was that gases are assumed to have no attractive and repulsive forces under kinetic molecular theory. And that's what made things ideal gases. We saw a little bit at the end of that chapter that the whole ideal gas law starts to fall apart if you get to lower temperatures or higher pressures because of the fact that you do get some attraction between atoms and molecules. Those attractions between atoms and molecules are different from bonds. Bonds is the sharing or transfer of electrons to hold the atoms together to form molecules or compounds. Intermolecular forces are the forces that occur between the two molecules, holding those molecules into a structure of a liquid or a solid. So in this case, you see here we have hydrochloric acid. The hydrogen and chlorine are held together by a covalent bond. However, the hydrochloric acid in the liquid form or the solid form is held together by the attraction between the charge on the hydrogen and the charge on the chlorine. It's an intermolecular force. You'll see here on this slide it also does mention that it is significantly weaker than a bond, and we'll see those values in a few minutes. So if you see a structure that's held together into its liquid or solid state, you have the positive side of an atom and the negative side of an atom being attracted to the opposite charge. So all of the red lines here are attractions, all of the blue dashed lines are repulsions. So you have attractions between opposite charges, repulsions between two of the same charge. But these attractions are what hold structure of a substance into that liquid or solid state. Now, remember from class today that we discussed that there are three types of intermolecular forces: dipole-dipole, hydrogen bonding, which we know is sort of a misnomer. It's not really a bond. It's an intermolecular force, and London or dispersion forces. Dipole-dipole happens between two polar molecules. To figure out if something is a polar molecule, remember that we need to look at the structure of that molecule, figure out if it has polar covalent bonds, assign the dipoles, the partially positive and partially negative charges, think about the shape of the molecule, and if it has a positive and negative side to the molecule, then we will refer to it as a polar molecule. Hydrogen bonding is the special case where we have a polar molecule that has hydrogen and either nitrogen, oxygen, or fluorine. This is a stronger version of an intermolecular force where you have the three most electronegative elements, nitrogen, oxygen, fluorine, being attracted to the positive charge on a hydrogen. And London dispersion is going to occur between non-polar molecules, and this is the weakest of the three. London dispersion a lot of times is the hardest for us to understand. We have nonpolar molecules. So in this case, an individual atom of hydrogen, or helium, sorry. Individual atom of helium. Two electrons around the nucleus, which has a positive 2 charge. Those electrons are in the 1s orbital. The positive nucleus of one atom could be attracted to the electrons in the other atom, forcing those electrons onto this side of the atom, which would then, the repulsion of the electrons from one atom would force the electrons on the second atom to the other side, giving us a negative side and a positive side. This is what's known as an induced dipole. One atom forces the other atom into a dipole. It is very weak, and which makes these attractions very weak attractions. Hydrogen bonding have some of the strongest attractions of intermolecular forces. We see in this case, we would expect the boiling point, the trend that we see between H2O, H2S, H2SE, and H2TE, we're going here oxygen, sulfur, selenium, tellurium in the group that is made up of oxygen. So they all have similar properties. We'd expect them to follow a trend. We see H2S, H2SE, H2T. The boiling point is increasing the further we go down the periodic table. But we see this huge difference with water. Water does not fit the trend. We would expect water, based on this graph, to be somewhere down here with the boiling point around, say, -20. However, the boiling point we know is 100. The reason for that is while these molecules, H2S, H2SE, and H2TE, are held together by dipole-dipole forces, H2O is held together by hydrogen bonding. Much stronger force, so the atoms are held together that much more strongly, which means it takes a lot more energy to get them to boil. You can see the same thing here with other atoms that show hydrogen bonding. H2O, H2SE, H2SE, and H2TE. Follow that trend. H2O doesn't fit the trend. HF, HCl, HBr, HI. The halogens with hydrogen, you'd expect a similar trend. You'd expect HF somewhere down here. It's not. It's up here because of the hydrogen bonding. NH3, PH3, ASH3, SPH3. Taking the members of the nitrogen family with hydrogen, you'd expect that to be somewhere down here, and H3 is up here because of the hydrogen bonding. So when we're trying to figure out the intermolecular forces within atoms and molecules, we can go through the following chart. Now we generally stick to the 3 intermolecular forces, which are sometimes referred to as van der Waals forces. But you also see ionic bonding on this chart because ionic bonding is really the similar type thing of an intermolecular force. It's just much, much stronger. So the first question, are there ions involved? If there are ions involved, we're looking at either an ion dipole force, which is sort of a mix of an intermolecular force and ionic bonding, or we're looking at ionic bonding. You have just ions. If there is not an ion involved, then we're looking, is it polar or nonpolar? If it is polar, if we can answer yes to that question, we have 2 choices. If it involves hydrogen with either nitrogen, oxygen, or fluorine, then we have hydrogen bonding. We answer yes to that question. If it's not hydrogen bonded to either nitrogen, oxygen, or fluorine, we end up with dipole-dipole forces. And if we answer no to the question, are polar molecules involved, then we're going to be London dispersion forces. The following chart gives us the strength of the various types of bonds in intermolecular forces. Remember, bonding is going to be a lot stronger than intermolecular forces. We can have ionic bonding, the attraction of a cation and anion. Look here at the energy, 400 to 4,000 kilojoules per mole. Covalent bonding, shared electrons, 150 to 1,100 kilojoules per mole. A little bit weaker than ionic bonding, but still very, very strong. Metallic bonding, which we did not go into a lot of detail with in this course, close, a little bit weaker, 75 to 1,000 kilojoules per mole. So here, remember, we're dealing with anywhere from 75 to 4,000 kilojoules per mole. If we go to intermolecular forces, ion dipole, that special case where we have an ion attracted to a polar molecule, there you get somewhat close to a bond, 40 to 600. Everything else you'll notice here is so much weaker. Hydrogen bonding, the strongest of the intermolecular forces, 10 to 40 kilojoules per mole. Dipole-dipole, 5 to 25 kilojoules per mole, weaker than hydrogen bonding. And then you can see the ion and dipole-induced dipole, some other versions of this. And then you look at your London dispersion forces, the weakest of the 3. You can get as low as 0.05 kilojoules per mole. The other thing we want to talk about at this point is phase diagrams. Phase diagrams are diagrams that show us the relationship between pressure and temperature on a substance. This is the phase diagram for water. You're always going to get 3 lines. You see your 3 lines, one here, one going this way, and one going out this way. Those separate your three phases of matter. You're always going to have solid in this section, in the case of water, that is ice, liquid in this middle section, and gas in this section to the right and down. As you cross over a line, you're undergoing a phase change. So if you go across the line this way, that is what we refer to as melting. If you go across the line this way, that is what we refer to as freezing. If you go across the line this way, this is what we refer to as boiling. Going across the line this way, condensation. Those are the common phase changes we're used to seeing. If we go to a standard pressure, we know that standard pressure is 1 atmosphere. The phase change for water from melting to melting or freezing happens at 0 degrees Celsius. The phase change boiling to condensation happens at 100 degrees Celsius. You also see the phase change down here going straight from solid to gas. We refer to that as sublimation. And if you're going back the other way, this is a term we refer to as deposition. If you think back to the lab that we did where we wanted to separate the various substances, we actually did a sublimation deposition process by heating the iodine, letting it evaporate to form gas, cooling it back down, and having it deposit on the evaporating dish. So anytime you're crossing a line, you're undergoing a phase change. And you can see at various temperatures and pressures, you have to get an incredibly low pressure, below 0.006 atmospheres, before water will undergo sublimation, and very cold temperature. Higher temperatures, you're more likely to be a gas. Higher pressures, more likely in those cases to be liquid or gas. And sometimes solid, depending on what the temperature is dealing with. You also see two unique points. This point, the triple point, is where a substance exists as a solid, liquid, and gas all at the same time, transferring between those three stages. And the critical point, this is the temperature above which the substance will be a gas. Any higher temperature will always be a gas, no matter what the pressure happens to be. So water, this is what works. If you're given a value, say we found that it's 2 atmospheres and 50 degrees Celsius. So 2 atmospheres, just slightly above this 1. 50 degrees Celsius here, we find a point, we would know we are in the liquid state. You could find any point based on temperature and pressure what state of matter it will be in. One of the interesting substances that we talked about in class a few times is carbon dioxide. Carbon dioxide, known as dry ice. It is dry ice because it goes from solid to gas, the sublimation process, at normal temperatures. Water we see here goes at very low temperatures, below 0.01 degrees Celsius, below 0.006 atmospheres of pressure. This is the phase diagram from carbon dioxide. You'll notice that the triple point for carbon dioxide is all the way down here at negative 564 degrees Celsius and 511 or 5.11 atmospheres. Our standard pressure of 1 atmosphere, you're going to see solid carbon dioxide for at a standard pressure, any of our standard temperatures. Let's say we have a temperature up here of 25 degrees Celsius, room temperature. So standard pressure, room temperature, we're out here. It should be in a gas. Dry ice is kept very, very cold, so it's kept at a very low temperature. So as you take it out and put it at room temperature, it goes across this line and undergoes sublimation. You have to go to a very high pressure to get the triple point, and to actually melt it to a liquid, you'd have to be above 5.11 atmospheres, 5 times the pressure here on the Earth's atmosphere, before you'd ever cross this line freezing melting line. So hopefully that helps a little bit with phase diagrams and a good review there of intermolecular forces. We'll continue to work on these in class tomorrow.